Pretty much. All right. So now we're entering the solid-state physics world and chemistry. And over this summer, I spent working in the Alivisatos group with my grad student Danny Publish, and we worked on studying solar cell materials, specifically Cadium Telluride. So what is a solar cell material? Well, simplistic model of a solar cell, you have a bunch of layers, your back contacts, your front contacts, and your absorbance layer. And the way it simply works is you have light come in, hit your absorbance layer, you get this excitation of these charges, and they're carried through by your contacts to an external circuit, and you power a device. So what we're focused on is this right here, the absorbance layer. So we're looking at Cadium Telluride as an absorbance material. Other materials are silicon. So when you talk about solar cells, you typically have to compare yourself to competition. The market right now is dominated by silicon. It's like 80–90% of the market. So we have to compare Cadium Telluride to silicon to sort of see what's the motivation of studying this material. So the first thing we really look at is the Shockman-Keysar limit, and that's pretty much the maximum theoretical efficiency of these materials given some sort of like solar spectrum. So what you see here is silicon, cadmium, telluride are pretty much comparable. But now we go down to like the lab efficiencies and the commercial efficiencies. So lab efficiencies are pretty much the most optimal device. They're really small scale, but like they're the highest efficiency that people have made. And you start to see this sort of disparity between silicon and Cadium Telluride. And now there's even more disparity when we go into commercials. This is the modules you put on your roof or whatever, your solar panels. You start to see even a bigger disparity between silicon and Cadium Telluride. So looking at theoretical efficiency and commercial efficiencies, there's lots of room improvement for Cadium Telluride. And that's good news for like a researcher such as ourselves, where we want to figure out how to increase these efficiencies. So to go even further than that, we look at why Cadium Telluride is just a better material innately. So it's a thin film technology, so it has the potential to cost less, and it needs less energy to produce or manufacture into these solar cells. And it also has this innate quality to have better high temperatures. So what does that mean? That means solar cells are thermally sensitive, so at higher temperatures they don't perform as well, they start to lose efficiencies, and silicon loses more efficiency than Cadium Telluride at high temperatures. So the second sort of motivation is that we're not just studying Cadium Telluride, we're studying nanocrystals. So compared to industry uses this method called PVD, or physical vapor deposition. Not really going to describe it, but this process requires high temperatures. It's like a batch-like process. It uses a lot of material, and it needs like a vacuum or low pressure. So essentially what we get is these large domains of Cadium Telluride film. And these are the absorbance layers you can use in your solar. So what we're proposing is this nanocrystal route, this alternate manufacturing route. So what is a nanocrystal? So a nanocrystal is times 10 to the minus 9 meters. So we're on the wavelength of light with these molecules. And essentially what a Cadium Telluride nanocrystal is you have these core of Cadium Telluride molecules arranged in this lattice, and on the outside of this core you have all these ligands. So you have, we call them sort of capping ligands, like they're organic molecules, halides or whatever. And the importance of these ligands is they keep our nanocrystals suspended in solution. And that's important because now what we have is Cadium Telluride suspended in solution, so we can spray it, deposit it, spin coat it, so we even print it. So we can essentially call this some sort of nanocrystal. And now we have a really easy deposition method that allows just heat treatment at a lower temperature, ambient pressure. You can do it in atmospheric pressure. You can do it as an inline process because it's a really easy deposition method, and it essentially will waste less material going from your nanocrystal deposited film to your ideal film. So taking it further than that, you need to understand sort of how solar cells work. So solar cells are essentially comprised of a bunch of semiconductors, and an important thing that sort of quantifies these materials is something called vacuum. So imagine you have two atoms. This is like a really simplistic hydrogenic model. We have one atom here, one atom here. They each have a valence electron, and they're unbonded right now. So you see them unbonded, one electron in each atom. So when they bond, what happens is these electrons occupy opposite spins. They can't occupy the exact same state by something called the Pauli exclusion principle. And now you have atoms bonded in these bonding orbitals that are lower energy, and then consequently you have these anti-bonding orbitals at these higher energies that essentially there's an energy gap between these two. So let's say we take another pair of atoms, bond them, another pair of atoms, and bond them. What you start to see is we're building up this solid lattice structure. So you approach infinite atoms, what you start to see is this continuum of discrete energy levels over time, or not over time, but every time we add pairs of atoms. And consequently, you see these discrete energy levels of higher energy antibody orbitals, and in solid state physics, we call these bands. So all our electrons are essentially in this valence band, we abbreviate VE, and then all our holes, or our lack of electrons, are this higher energy state, or our previous are antibond orbitals, and this conduction band, or CB. And what we have between them is this sort of energy void, or this band gap. So there's this gap of energy between the top of our valence band and the bottom of our conduction band. And that's essentially what a band gap is. So keeping that in mind, we can use this concept to sort of describe how a bunch of different types of materials behave. So if you have something called a conductor, what essentially you have is an overlap between your valence and your conduction band. So essentially, your charges or your electrons and holes can move freely throughout your material. So this is something like silver or gold. It's a really good conductor, so it's really good at moving charge around. Take the opposite case. Now you have a really large band. You have a large energy void between your valence and conduction band. So it takes a lot of energy to excite any electrons from your valence to your conduction band. And that's essentially an insulator, something like glass. You don't really see it conducting very much. Now there's this intermediate thing called semiconductors. Now you have something that's small enough band gap that you can have optical or thermal excitation from your valence to your conduction band of these electrons. And essentially what that causes is, let's say you have a low energy light pass through your semiconductor. If it's less than your band gap energy, you get no electron excitation, no absorption. Okay? So if we take that same material and we put higher energy light, something like UV light, violet light, whatever, some higher energy light that's greater than or equal to our band gap, we get this excitation of the electrons. So I'll show that one more time. If you watch closely, you get this excitation of the electron from the valence to the conduction band. Now what you can use, if you hook up an external circuit, you can have electron and hole flow, and now you have a current. So now you can extract the charges. Now we're excited via light, and this is called the photovoltaic effect. So now back to my research. That was just all background. So first thing we have to do is make these nanocrystals. We start out with our cadmium and our tellurium precursors, and we use something called the hot injection method. Heat them up, inject our tellurium in, and essentially what we get is our tellurium precursors combined with our cadmium precursors, and we end up with these cadmium nanocrystals capped by these sort of soap molecules. And I can call them soap molecules because if you look down here, they have these like hydrophilic heads and these long hydrophilic chains, typical of things you find in soap. And we end up with our little vat of nanocrystals. And what's really interesting about this technique is that it's very time sensitive. So over time, our nanocrystals grow. And because they're on the nanoscale, it sort of obeys this sort of rule called quantum confinement. And essentially what that is at smaller scales, our band gap is larger. So what that means is you need higher energy or lower wavelength light to excite our electrons from our valence to our conduction band. And over time, these crystals grow to larger and larger nanocrystals to be almost bulk-like, and they have a smaller band gap, which essentially means lower energy or higher wavelength light. So you can actually visibly observe this in the reaction. So over time, actually a very quick reaction. So you see a quick color change through the visible spectrum, and you see them go from across the visible spectrum. So this was captured a little later in the reaction. It wasn't that great, but you can actually see it go from purple to blue to green or whatever. We take aliquots all the time. And with these aliquots, we do some UV visible light spectroscopy. And what we do is we can actually quantize the size of these nanocrystals based on this absorption peak. So this absorption peak correlates with some sort of energy, and that energy is the band gap. So that first absorption peak is that first point where we have electron excitation, and that's how we quantify our band gap. So over time, you see these band gaps shift over and over and over, and that's just correlating with our nanocrystals growing, and over time again, our nanocrystals continue to grow, our band gaps get smaller, and we end up approaching this bulk-like nanocrystal. So that's important because now we can choose what size nanocrystals we want and have control over our band gap when we're making a solution. So after we have these nanocrystals, we have these large soap molecules, we use some chemistry, get these amines and chlorines on top. It's just empirically found that these chlorines improve efficiency a lot. It's still not understood why. And then we just put our nanocrystal solution in vacuum, strip off these organic molecules, and now we have a purely inorganic structure. So our cadmium core with our chlorines on top. So we do some really quick tests with these chlorinated surface cadmium chloride nanocrystals, and we see that our band gap is unaffected. We do some transmission electron microscopy, and we see these are the soap molecules, the large organic molecules. You see how Pauli dispersed they are. They're all uniformly dispersed. They have these large gaps between them. When we strip those large molecules and put the amines and fluorines on, you start to get this clumping or whatever. These nanocrystals are much more compact, and that's just a characteristic of these small molecules. So now we have our solution. We can use something called a spin coater. It's like an ink or whatever. We just take our cadmium telluride ink, deposit it on our spin coater, spin it really fast, let it dry, and now we have a cadmium telluride as deposited thin film on a silicon substrate. And this is important because we can pretty much correlate the thickness of these films with the spin speed. So now we have another variable we can control. So we do atomic force microscopy to quantize how thick these films are, and you get this sort of power correlation. And then now we have these as deposited films. We thermally heat them or treat them, and we start to get these larger grains and domain growths, which are really important for electrical conductivity and performance and other such things. And essentially what you can do is, these are scanning electron microscope images, so this is a different technique than previous. But we see this is 90,000 times magnification, this is only 60,000 times. So as deposited, these are, you can't even like make out how small these nanocrystals are, but you start to see these large domains at a lower magnification. So this thermal annealing really grows these crystals into larger sizes, into these larger annealed particles. And now what we do is we just do another quick atomic force microscopy test, see the thickness of these films after annealing, and what we see is that there's a drop in thickness after annealing. That's really easy to sort of explain. You have nanocrystals are sort of loosely packed or whatever, you heat them up, they start to coalesce and become packed tighter, so thickness essentially decreases. And now we have our annealed films, and this is sort of where my research is at now. And what we want to do is we want to test the optoelectric properties. We want to see how this absorbance layer we've made from nanocrystals now to that comparable like industry like cadmium telluride thin film. And we want to see how well it conducts, how well it can carry a current, how well it photoconducts, how well it carries a current when you shine light on it, and how well it has like this charge carrier mobility. So how well electrons and holes can sort of move through your material. And we've done some initial field effect transistor FET tests. We've got some initial low conductance just because cadmium telluride has some empirical results, like the contacts that we're using are gold, and there's other such things that we should try out. And these are just preliminary results that we're going to work on in the future. So that's pretty much it. I want to thank my grad student mentor, Danny Helbut, that's here right now, for, I didn't know any of this before. I mean, I didn't know any solid-state physics, so I learned a great amount this summer. I want to thank Professor Paul Alivisatos for welcoming me into this group, a few members of the Alivisatos group who helped me with spectroscopy, Noah, Matt, and Brandon, and then the rest of the staff, the donors.